All right, let's get started. Thank you everybody for joining this webinar about secure offline updates with Toradex Torizon OS. My name is Mohammed Bilou. I'm the CEO of Mab Labs Embedded Solutions. So just a little bit about myself first. I'm an embedded software consultant based out in New York City in the United States. My main focus is in design work. I've worked on projects that span a number of different verticals, including medical devices, scientific instruments, LiDAR systems, and I've also helped develop custom ASICs. My core experience and expertise has been in embedded Linux, the Yocto project, and Zephyr Project RTOS recently. I encourage everybody to shoot me an email if you have any questions. You can connect with me on LinkedIn. This is my handle here, and follow me on GitHub with using that my handle over there. I also encourage everybody to sign up for my BIOS Food newsletter. You can sign up using the website www.mab-labs.com, or you can scan this QR code. I provide number of updates regarding training and workshops. A few weeks ago, we had an in-person training event around embedded Linux, the Yocto project, specifically targeting Toradex boards. We're going to have ongoing training and workshop events focusing on embedded Linux, Yocto project, and also we're going to be hosting training events on Zephyr. So if you're interested, I encourage everybody to sign up for my newsletter to stay up to date on future events. So today's agenda is first, we're going to get started with understanding what the whole motivation behind secure offline updates is. Then we're going to take a step back and understand how Torizon remote updates or online updates work, some of the underlying frameworks that Toradex and Torizon have leveraged in developing their remote update mechanism. And then we're going to talk about how Torizon, the secure offline update feature works in relation to the remote or online update feature. Then we're going to go through a demo showcasing the process of deploying an offline update first. How do we build it? How do we deploy it to the cloud? And then how do we retrieve it from the cloud so that we can place it on a flash drive? Um, and and then actually deploy it to our device that's out in the field that doesn't have any sort of internet connection, really. And then we're going to talk just conclude with some next steps. So first, let's talk about motivation, why just updates in general, why secure offline updates are important. As we probably all are familiar, the importance of having over-the-air updates is that it, quote unquote, allows us to easily update the firmware on our device. Now, the term easily is a bit loaded. We're going to talk about why that is in the next slide. But in general, right, if you don't have OTA updates, it makes it really difficult to push firmware updates that if we want to add features or if we want to resolve issues, it becomes very difficult to push these updates out to devices that are out in the field if we don't have an OTA update mechanism. And as you're all probably aware, our work is never done as embedded software engineers. We always, from the product team, they're always looking to deliver the latest and greatest in terms of their product, and that includes a number of feature additions that, of course, need to be implemented by embedded software engineers. And so, these feature additions are mainly driven by business decisions, and as as the competitive landscape progresses, right, our product always wants to push the boundaries, and so that's why we always want to, for the most part, add features. And we also want to make sure that any bugs that have either been discovered by our team or that have been reported by customers, right, that we've addressed those issues as well, and we've deployed fixes to those issues as in the form of a firmware update. Recently, the EU Cyber Resilience Act has become a really hot topic, and that requires that there be a defined mechanism where security vulnerabilities discovered by the team or discovered by external entities, right, that resolutions of these vulnerabilities are pushed out to the devices that are out in the field. So that's becoming an increasingly hot button topic that drives the motivation for having some sort of OTA update mechanism. So in this last slide, I said that OTA updates allow us to easily update the firmware on our device, but the problem is that there's so many nuances and so many challenges that OTA itself isn't easy because we need to account for many factors, right? So you probably have heard the term or the phrase, you don't roll your own crypto, right? Because there's so many considerations that need to be taken into account surrounding safety and security. In a similar vein, right, you don't want to roll your own OTA. You want to leverage proven, mature, ideally open source frameworks that you want to build your own OTA off of, right? And some of the considerations that we need to take into account when developing or considering an OTA feature, an OTA framework, is security, right? So encryption, authentication, signing, they all fall under the umbrella of security to make sure that the devices that have that are target for updates are actually valid, that the update itself is also valid, that nobody's trying to maliciously install or can install an update that they're not authorized to on your devices. Reliability is another key factor when developing an OTA feature, an update feature, right? So we want to make sure that our updates are atomic, right? That there's no point in time where any process is so lengthy that that'll necessarily we're trying to minimize the possibility of breaking the device essentially, and that's what reliability means, right? So atomic updates basically try to minimize the amount of time where breaking is a possibility. We also want to incorporate some fail-safe mechanisms to ensure that, hey, if let's say a failure, if there's an update and there's a failure in the update process, that we have a built-in mechanism to make sure that either we can revert to an older version of our software, or there's some other there's some other mechanism in place that makes sure that we don't end up with a brick device. And also validation, right? That like it kind of falls hand in hand with security to make sure that that the image that we're updating to has been validated to some degree or through some process. Modularity is another important consideration when evaluating different OTA schemes. So what that means is, does it have a capability to support Delta updates? So you're not just basically downloading everything unnecessarily. You're only downloading and fetching components that have changed, right? Is there some sort of version control system that goes hand in hand with these Delta updates? And does the framework that you're using have some sort of dependency management system to ensure that that if there are any changes in the dependencies of the changes that you want, that those are also captured as well, and you don't need to kind of manually and externally be responsible for other dependencies, right? Some other considerations that we need to keep in mind when we're evaluating different OTA frameworks and mechanisms is bandwidth optimization. In a lot of in a fair number of devices, right? You can be in a scenario where your internet connection may not be ideal, right? Maybe pretty spotty. You may not have the throughput that you would require for some really lengthy and long kind of update processes. So in that case, you want to select a framework where it can optimize the bandwidth, and it can also allow you to target specific devices. So you have some sort of access control for devices that are kind of out in the field. And finally, right, we just talked about just OTA updates in general. But what about devices that don't have an internet connection, right? So this can be driven by domain requirements. In a few medical products that I've worked on, they have a strict requirement where, there is no Ethernet port. It's physically removed from the device from a hardware point of view because it's a requirement not to have that during deployment. And there are other kind of functional safety domains where there may be explicit reasons why an internet connection is not made available on the device. So in air gap solutions, for example, there's an explicit requirement where an internet connection is not available. Or let's say, there may not be an explicit requirement for that an internet connection isn't available, but just by the nature of the deployment, right? just having an internet connection is maybe a luxury, may not even be possible, right? So if, let's say, your device is on an oil rig in the middle of the ocean, right, where there may not be an internet connection for long periods of time, but you still would want to have some sort of update mechanism in case you need to push out a feature or bug fix, right? You still want a mechanism to perform updates. Also, for example, like inside an elevator shaft, right? Sure, there may be internet in the building, but it may be really difficult to get an internet line or even a Wi-Fi into the elevator shaft. And so you need some other mechanism for a human to be able to plug something in, like a USB drive or a flash or an SD card, right, into the system to be able to update our system, right? So this is kind of the crux of what we're going to talk about today, about how, if, let's say, a device doesn't have internet connection, how can we still allow it to leverage, some of the considerations that we talked about in the previous slides, when doing an OTA update, but without having an active internet connection. Right. So Torizon, has already in place a mature kind of remote update mechanism. So this is a feature in Torizon OS that enables OTA updates, and it's built on mature frameworks. So these frameworks have been selected because they satisfy the concerns that I kind of talked about in the previous set of slides. So the two big frameworks are OSTREE, which is responsible for managing the underlying root file system of your board, of your device, and Uptane or Aktualizr, which is the client implementation of the framework, of the Uptane framework, which is responsible for the reliability and the security of the updates to make sure that, hey, that the device is downloading a reliable update package. It's verified that it's not malicious, etc. So these are the two key frameworks that we're just going to cover in a little bit of detail today, that pin the underlying the core foundation of Torizon's OTA update mechanism. So let's talk about OSTree in a little bit of detail, right? So technically it's known as libOSTree because it's more of a library. And it really relies on a single partition scheme, right? Other frameworks use multiple partition scheme. Usually you'll hear the term dual AB partition scheme. We'll talk about what the advantages of OSTree over a dual AB partition scheme in a later slide. But OSTree is effectively, if you imagine, if you've used source control, right? If you use Git in the past, OSTree is really similar to having a Git-like model representing your root file system. And the advantage of having that sort of model or that sort of mechanism is that you can have updates you can have updates provided at a file level, right? So you don't have to update an entire partition and consume a ton of storage on your flash device. Having OSTree have updates captured at the file level tremendously reduces storage on your device, and it also reduces the bandwidth that are necessary because, again, you're only sending updates of individual files and not of entire partitions, right? It reduces the required bandwidth of the update mechanism significantly. The other kind of feature of OSTree that's relevant is that you can have, again, because your updates are on or are more so on a file level than on a partition level, right? You can have multiple software revisions present on the device simultaneously. And so the advantage of that is that you can have a known good candidate that already exists on your device, right? At some point you must have updated the device or you must have flashed an initial image onto your device, and that becomes your baseline image. And then all you're doing is essentially piggybacking off of that baseline image with updates through this OTA mechanism, right? And so you're guaranteed to have some known good rollback candidate that exists on your device in case an update fails, and you're guaranteed to have success in rolling back to a known good version and then not updating to a potentially faulty version. OSTree also supports directory exclusions. What that means is, so all of the like I said, OSTree is follows a Git-like model where your entire file system is essentially like a tree structure, right? With history like you would have in Git. And so what that entails is you really can't make direct changes to the file system itself, right, directly as you would on a normal Linux-based system. But you can exclude certain directories from this tree structure, and so which you can then make changes to these directories directly, so you can preserve user data or have consistent configuration. So, for example, if you wanted to make sure that, let's say, the etc directory was not part of your OS tree, then you could exclude that from the OS tree configuration. The other feature of OSTree is that you can have multiple bootable file systems stored in a single partition. Again, because we're operating updates on a file level instead of on whole partitions, you can have multiple instances of a bootable file system all in one partition, and there's no need. And what that does is you can have many different revisions of the same file system without sacrificing an enormous amount of space, right? So like I said, in OSTree, your file system is a repository. So what that means is if you're familiar with Git, it's essentially an object store with branches known as references, right? And you can manipulate the file system using commands similar to Git. And you can use the OSTree user space tool to accomplish that. And like I said, you can manipulate the file system repository right on your system. You can actually try that out, try the commands out that we're going to talk about in the next couple of slides on a like a test Toradex device if you have, or something sitting on your bench. I would not advise you to execute these commands on a production device because you're most likely going to break something. So this command, if we it initializes just an OSTree repository on our system. So you can imagine this is similar to just doing a git init in some sort of source control repository. Initializes the git initializer repository, right? And then we can, let's say, if we made a directory called tree and then echoed the hello world to tree/hello.txt, then we have a file on our system, right? And then we can commit this particular directory and the files underneath that directory in a branch called foo using this OSTree command. And then once we do that, we can execute the refs subcommand to list all the branches that are available in our tree. And here we can see that we have foo. And then again, right, because OSTree is operating on a file level instead of like Git where it's something different. It's in Git, it's just strictly objects, right? Because files are core to OSTree's management system, right? We can just run typical file commands as well as part of OSTree. So if we do OSTree -- repo and then run the ls command with the branch that we want, we can see that we have a hello.txt file underneath the root of this OSTree branch. And then if we cat the contents of this file, we can see that hello world is there. The other, right, similar to Git, the other thing we can do is actually check out a branch. So in this instance, we've checked out the foo branch underneath the tree checkout directory. And then we can cat the contents of this file, and we can see that it's hello world. So what this is demonstrating is if we wanted to change, let's say we wanted to have different files or different file contents, right, across different branches, you can kind of validate that, hey, if let's say I were to check out, let's say, a bar branch, right, and instead of hello world, I wrote hello world v2, and then I could switch back and forth between the foo and the bar branch. And if I were to cat the contents of this file in these different branches, I should see the different messages in these different files. So like uh, other file management systems, right? OSTree also has automatic rollback, right? So for example, if a device resets n times, OSTree supports a mechanism to revert to the last commit. And this is handled through U-boot environment variables like other sort of schemes as well. So you have an environment variable to count the number of resets. And if the number of resets exceeds a particular threshold, OSTree is instructed by the bootloader by U-boot to revert to the last commit. So some of the environment variables that are part of U-boot that interact with OSTree are reboot count, threshold, and whether or not we want to revert or not. So let's say you go through the update process, right? you reboot into your system. OSTree detects that, hey, my reboot was successful because I didn't enter a boot loop, right? There was no kernel panic, there was no critical failure of my system. So what OSTree does is it resets the reboot count environment variable, and in addition, it also resets whether to revert our image. It resets that environment variable. So these handful of environment variables are critical, not just for OSTree, for any sort of update mechanism. So one of the advantages of OSTree is that updates are immutable and they're atomic. So like I said, right, OSTree is similar to Git in that each update is a commit in the OSTree itself. So if let's say you're making a change to a file, right, the change to the file is encapsulated in a commit. Um, but each file is at the base level an actual file underneath, but it's not propagated towards across all updates themselves. And so there's a hash associated with each commit, again, similar to Git. The entire OSTree repository, it's placed in a single location. So again, you don't have multiple copies of the same files or the same file systems on your system. Instead, you have one repository that contains all of your files. And then you have different deployments that are represented by hashes. And if you have, let's say, specific changes to a file, then that change is encapsulated in that hash. But let's say in one particular deployment, you only have one change to a file, right? All other files are not duplicated, right? So what that means is the way that's accomplished is we use hard links, right? Which is very minimal. There's practically minimal overhead when using hard links. And so what you do is if let's say a file hasn't changed in a particular deployment, you just make a hard link from that deployment into the repository to the file itself. And so as you're making more and more deployments for files that haven't changed, right, you're just increasing the hard link to the underlying inode in the file system. And so what the significant advantage to that is you're not just copying files over and over again, which contributes to why you can have so many deployments on your system. Instead, all you're doing is just adding a hard link to files that haven't changed in a particular deployment, right? So the overhead is just the amount of overhead in creating a hard link, which is significantly less than if you were to essentially have duplicates of files. And in turn, right, because you're not having like unnecessary duplicates of files, and each commit is essentially a deployment. This contributes to speed, right? Because you're not downloading or fetching an entire partition. You're just fetching whatever changed from one deployment to another, and only the differences are updated. So, like I said, if let's say in one particular deployment, right, one particular commit, a single file changed, and let's say you have 1,000 files in your file system, right? The files that didn't change, all you're going to do is create hard links in your deployment directory to the underlying inode. And the only thing that's different is just the file that changed, right? And so, let's think about the process, right, on how this update mechanism works. You're downloading the update, right? You're only downloading the difference in the update to the file that you're targeting in that deployment, right? You're just incrementing so that doesn't take that much time, right? Depending on the file, it could, but for the most part, right, if you're implementing your commits correctly, right, the changes to the files are not that significant, and it's not an entire partition that you're updating. So you're just downloading that into a deployment directory. You're just incrementing the hard links to things that haven't changed, which doesn't take that much time. It doesn't take that much computational resources. And then the last step, right, is you're just updating where the RFS pointed to by your system is through an environment variable. So all of these steps are not that don't take significant time, right? And also there's very minimal exposure to when you can potentially break a device. So let's say you're in the event of, let's say, a power off, right? So let's say you're going through the process, right? You're at the last step, right before the last step when you want to swap out the RFS, and let's say you lose power. Because you didn't actually go through the process of updating the RFS, right? Your existing deployment is still there, and just all the new hard links have been updated, right? You're not going to actually revert to the newer deployment. You're not going to update to the newer deployment that's already downloaded on your system. Instead, when your update system boots into the older system, right, into the older RFS, detects that, hey, I've downloaded everything. All I need to do is just this last step where I'm just updating the RFS. That's the only thing it needs to do. It doesn't need to go through the whole process of updating the entire partition again. It can just swap out the RFS for the new one, and you're ready to go. So how can we compare OSTree to, let's say, a dual AB partition scheme? Well, in the AB partition scheme, right, you're using two partitions now, and they have to be both partitions have to be of equal size. And so usually the way the process works is you're updating the inactive partition while the active partition is being used. So you're writing directly to the underlying flash of the inactive partition. And so the problem with doing something like that is you know, you may need to store, let's say in the middle of an update, you lose power, right? So either you can start over again, which is inefficient, or you need a mechanism to tell your update mechanism, okay, where did I last leave off? And then resume from that again. And then but you still need to have checks at the end to make sure that, hey, that nothing is corrupted again, because you're just writing to direct memory, right? You're writing to just the raw underlying flash system. So, you need to add some additional overhead, some steps to make sure that, hey, what you've written is valid, right? That you can actually boot into it and that it's complete. But also the other significant disadvantage is because you have two partitions that need to be of equal size, you're effectively reducing the overall flash space by at least a half, right? So in other kind of schemes, right, you also want to have some sort of persistent partition, right, that is relevant for both of the A and B partitions. And so in that case, that may contribute to less than half of the partition of the flash size being available to both partitions, right? And like I said, because you're downloading and you're flashing the entire RFS for for one whole partition, right? You need to download that. So that's going to take significantly longer because you're downloading duplicate files that you may not necessarily need. But again, because of the underlying scheme, you have no other choice. So OSTree, in my opinion, is just more performant. It's more optimal when compared to traditional A/B partition schemes. So we talked about OSTree and how it kind of manages the underlying infrastructure of the RFS. Now let's talk about the actual update kind of framework itself, right? Including the actual client side implementation. So the update framework itself is called Uptane. It's a secure OTA or SOTA update framework. It was originally developed for the automotive space. And essentially the way it works is you have multiple microcontrollers or ECUs on your vehicle, and they kind of interface to the primary ECU to manage updates to their own firmware, right? And the Uptane framework uses multiple servers to validate data before update starts. So again, you have multiple instances of the images that are present. They're signed by different servers, and so you can validate, let's say, an image from one server with the image from another server to make sure that to pick an appropriate server and to mitigate any attacks on single servers and on any single server. You can also mitigate attacks on potentially all servers, right? If, let's say, none of the servers, none of their signatures match what you're expecting, then you can just reject all updates from all servers, although the device will never receive an update, but there is some precaution in place to ensure that that you're not just you're not inherently just downloading malicious firmware that you haven't verified. So some of the design principles surrounding Uptane is that one, separation of trust. So you're distributing the responsibility of signing metadata, like I said, across different servers. So if, let's say, one signing key is compromised or even a handful, if you have enough servers, right, you can be guaranteed that, hey, if a multiple signing keys have been compromised, then you can still retrieve your images, and you can verify those images from other servers as well. There's also this concept of a signature threshold. So what that means is you need basically you're kind of crowdsourcing the verification process, right? So you reach out to different servers, you get a number of signatures, you verify these signatures, and once you've exceeded a threshold of signatures, of verified signatures, then you can say that, hey, okay, this image, it looks good, right? A couple of different servers that I trust have verified the authenticity of this image. All right, we're ready to go. We're going to start the update. We're going to start downloading the update. And then there's also a provision in place for key revocation. So if let's say a device identifies that, hey, this server, there's something wrong with the server's signing key, I'm just going to ignore it. And that's implicit key revocation. Or you can just eliminate the server, remove it from your pool of trusted servers. Or let's say as an admin, you've discovered that, hey, one of the servers that are signing the images, they've been compromised. So I'm going to explicitly remove that key from the trusted keys that devices use to authenticate and verify. So this is a mechanism that this diagram just shows how that process works in the context of, let's say, the automotive space. So Uptane kind of balances both security and speed by using what are called different repositories. So in the case of, let's say, security, you have multiple servers that are acting as your source of image repositories, right? So each image repository contains an image and metadata, and these images and metadata are signed using offline keys, right? So there's some security built into it that these keys are never made available, right? But again, if let's say a key is compromised, because there are multiple servers that are using offline keys, you can essentially blacklist one of the servers that have been compromised, and then still rely on other servers that are still valid to be able to provide images and updates. And then there's the director repository, right? And it instructs devices about which update to apply, and it's using online keys to sign metadata. So what ends up happening is, let's say in this case, the primary ECU reaches out to the director repository, or is told by the director repository about which update to apply. And there's metadata that goes along with it. So the device kind of makes sure that the metadata has been correctly signed. If it has, right, if it verifies the signature, then it can immediately go out to an appropriate image repository and immediately fetch the appropriate image, making sure, again, that the signature from the image repository is a verified signature as well. So, like I said, the device also has a fair bit of verification capabilities and responsibility on their own side when using Uptane. So the device checks the image metadata itself to determine if it's safe to download. It does that by retrieving an image from the image repository. It calculates the image hash, and then it compares the signed metadata in the image against what the metadata was reported in the director repositories. And if it matches, then it starts the download and update process. So Uptane is the framework and the entire kind of protocol surrounding the update, like secure and reliable updates. Aktualizr is the implementation on the device side that is responsible for interacting with the servers that implement this Uptane framework. So Toradex actually forked the upstream variant of Aktualizr to support a number of different um, uh, enhancements to support use cases for Toradex customers, right? So one of the big things that is obviously relevant to this webinar is offline updates, where, again, updates can be made to the device, right, without necessarily having an internet connection. Toradex also implemented an enhancement where if you've used Torizon, right, you're familiar that all applications are generally inside a Docker container. right? Since it's one of the best practices to be able to allow different containers, different applications to be run in their own sandboxes, right? So Toradex has applied this enhancement to be able to support OTA of Docker containers. And again, if you think about the use cases of that a lot of Toradex customers use their products, right? It's you would want to also update components that are not in Docker, right? So if you have, let's say, a bootloader, right? Let's say you want to try to update U-boot, and obviously it's not in a container, and it's not in a container, and it's not just a typical file in your file system, right? You need a mechanism to be able to update U-boot, right? And also having this generic mechanism allows us to write our own sort of handler and to be able to update different components and update different firmware of different components that are running on our system, right? So if let's say you have firmware running on an ARM Cortex-M, for example, on your SoC, if you have these handlers to be able to update any generic firmware, you can then update the firmware that's running on this other kind of coprocessor. So to summarize kind of Torizon just remote online updates, right? So we gain this efficiency via OSTREE, where we're not wasting flash space because we don't have to have two partitions present on our flash disk. Where again, because of the underlying framework of OSTREE, there's minimal time when we're updating because each deployment is ideally really small and constrained to a single sets of files, right? It's not an entire partition, so there's minimal downtime when we're performing an update. We have the security and reliability that's offered to us by Uptane, and also the flexibility via Aktualizr. So Aktualizr, just in general, right, supports entire OS updates, but also through Toradex's enhancements, we can also update applications that are encapsulated in a Docker container, and also just components that are not in Docker. For example, a bootloader, or let's say firmware that's running on an MCU, we can also update the firmware that is running there through Aktualizr. So how does secure offline updates work, right? So we talked about remote online updates, but what about secure offline updates, right? And it's really no different, right? It leverages the frameworks that we just discussed previously. It still has OSTree, it still has Uptane and Aktualizr. The only difference is that there's this concept of a lockbox, right? That's introduced by Toradex. And what it essentially does is the USB drive, right? The data contained in the USB drive is essentially emulating the server that's sitting in the cloud, right? And the device, if it has support for offline updates, it goes through the same exchange that it would conduct when it's communicating with the server, but instead it's just validating the data that's on the flash drive itself, right? And so essentially you have the same advantages of OSTree, Uptane, and Aktualizr. The only difference is that the medium, right, is just different. Instead of having an internet connection, it's just a server you just have files that the server would normally emulate when you're talking over the cloud connection. So now let's quickly kind of talk, I'll just showcase the demo that I kind of put together to demonstrate this. So just a quick overview of the demo. I'm using a Colibri i.MX 8X on an Aster carrier board. We have a baseline, so I created a baseline Torizon OS image with a Hello World kernel module. I called it Secure Offline Update V1. I pushed that image to the Torizon cloud. You don't have to do that, but just a good practice that I just follow. And then I installed the baseline Torizon OS image onto the board via Toradex Easy Installer. And then I confirmed the presence and execution of our kernel module. And I forgot to mention that we also need to apply some customizations to this image as well to allow it to enable offline updates as well. Okay. And then the next step is, so we have our baseline image one, which enables offline updates. Now we want to modify it, modify the kernel module so that a different message is printed to the kernel log, right? We create a new Torizon OS image and call it V2, right? We push that to Torizon Cloud. This is necessary because now we can access that image through our lockbox, right? And put it in our lockbox. We create the lockbox in the Torizon Cloud. We download it to the flash drive using Torizon tools. We plug in our flash drive to our Colibri board and then just watch update process in the terminal. Once the device reboots on its own, right? The device is going to reboot on its own. We can log into our new deployment, load the kernel module, and confirm that we have the new message that's printed that we've added to our kernel module. And before we get started, like an important thing that you have to keep in mind is you have to download your credentials.zip if you're following along. So you can do that through the Torizon Cloud web interface, right? Because we're going to be using this to push our images to the Torizon Cloud. And right, so this video kind of just shows the process of going through, right? So just setting up the Torizon Core Builder. So here we can see we have a pre-downloaded easy installer image. First, we're going to just download the setup script to set up our environment. So tcb-env setup.sh. And then the next step is to source the environment file. And what this process does, it pulls, it's essentially setting up your Docker container to run the Torizon Core Builder tool, right? And so you have to source this environment file every time you open a new terminal, just to make sure you keep that in mind. In this case, because I've already downloaded the container and have it set up. Once I source this file, I don't need to go through the download process. It's just ready to go. It's just setting up my environment. And that's all I need to do. But the first time around, you'll notice that when you run this, it's going to take a bit of time because it's first spinning up the container and downloading all the dependencies. And in this video, we see that, okay, we're going to create an images directory, going to go into it, and then we're going to download the baseline Torizon image without any pre-provisioned containers into our local kind of images directory. And this is specific to the Colibri i.MX 8X. Okay. And so now, so to test out our kernel module, Toradex provides an out-of-tree kernel module just as a reference example. So we're just going to clone that. So we're going to clone that as the next step. And then the other thing that we need to do is create the YAML file that's associated with our container. So this is not complete. We're going to see the complete YAML file in the next slide. So what this is doing is it follows a really strict format. So we have an input, right? We define what our base kind of raw image is going to be, right? With Torizon, just the base raw image from Toradex that just contains Torizon. And then the next section defines like what our customizations are. So in this case, we've specified a kernel module with this particular source directory, and we're telling Torizon not to auto-load our kernel module because we just want to do the loading after the device is booted into the new image. And then the last section that's important is the output, right? So again, we're specifying that this is the name of the image. This is the name of the directory where the image contents are going to be stored. And this is the name of the image itself that's going to show up in Easy Installer. Okay. And like I said, so this is still not complete because we need to enable support for offline updates. So the first thing we need to do is we need to download shared data, right? Again, there's a component on the device side, right, that needs to be present to ensure that when we plug into Lockbox, that the images and the metadata that are on the Lockbox are indeed valid. And that's where the shared data comes in. So this is something that we retrieve using the Torizon Core Builder from our Torizon Cloud instance, right? And we use our credentials, right, to download this data. And this is going to represent the information that the device is going to use to verify the image and the metadata in our lockbox, in our flash drive, right? And so the other important thing that we need to do is make sure that we enable support for all offline updates. So we can do that using a TOML file that's located under user lib soda conf.d. And so what we're doing is all we're doing in this TOML file is just saying we want to enable offline updates. We set that to true, and we disable online updates. And then we tell it where to retrieve or where to look for any of the offline updates that are going to be present in our lockbox. So I formatted my flash drive and I called a partition on it lockbox, right? So I'm guaranteed that the partition or this partition is going to exist, right? And so we can, what we're going to do is we're going to have to place all of our update content, right? Our update artifacts under this, under the root of the flash drive, and then we can plug it in. And then what we need to tell the Torizon core builder is that, hey, this directory structure, this user lib soda, we're going to add this directory structure into our file system, and this is going to be present as an overlay, right? So because again, OSTree, you can't directly modify files in OSTree. You need to add overlays because that's not how it works. It's not a traditional kind of file system, right? It's a repository, right? So you know, if you imagine like when you're using Git, right, you don't modify the Git like objects directly, right? You're using Git commands to be able to modify the tree itself, right? So in the same vein, right, you're using you can't directly modify files in the OSTree file system, right? Instead, you have to add files or make modifications through this image itself, right? And you can do that through the Torizon core builder. So what we've done so far is, you know, we've instructed. So just to summarize, right? Our input is the baseline kind of easy installer image, right? To baseline image for Torizon with Docker support, right? But with no pre-provisioned containers, right? Targeting the Calibri i.MX 8X. We have two customizations. The first is we want to compile and add a kernel module called hello that is contained in hello mod in this directory. And we also want this directory structure contained under the changes directory, where essentially the file system will contain user lib soda conf.d99 offline updates.tml.toml. And then finally, we want to create like an image called in this directory, right? Map secure offline update v1. The image itself is going to be called secure offline update v1. We're going to have it provisioned for offline mode. And this is the shared data that we're going to embed in the device, right? So that it can validate images and metadata that we want in our lockbox. So let's see that process in action. So in this particular case, first we're gonna, I forgot, I inadvertently placed the hello mod directory under the images directory, which is wrong. So I want to move that one level up. And then all I need to do is do Torizon core builder build, and it's going to chug along. It's going to parse the configuration YAML file. It's fetching, again, because I've already downloaded the image, right, in the previous step. It didn't need to go and fetch out. It was able to retrieve it locally. And now it's building the kernel module, right, located in the directory that I specified. Now it's building, and it successfully built the RFS. Okay, and then when I run easy installer on my Calibri board, you can see that you know it showed up, right? The name that I specified in the TC build YAML file, it showed up in easy installer, and that's actually, I really appreciate this feature, because if you've done a bunch of these updates, you know that it can be really hard to distinguish between different images that you want to update to. And so this makes it really easy for me to easily pick off which one I want. And so after going through the easy installer process, I boot into my new board. We wait for the system to load. And again, this is all over a console interface through Minicom, because the device doesn't have an Ethernet connection for the sake of this webinar. And so I'm just remoting into a Linux PC that has a connection to the console, to the Calibri console, right? So we're waiting for the system to boot. And I've already changed. So, if you've used Torizon before, you know that when you first log in, you're forced to change a password, the default Torizon password. So I did that already. So I'm not going to be prompted for that. And after I log in, I can, I need to go back and I need to see if I check in hello mod, right? The actual kernel module name is called hello, which is because it's hello.ko. So I can just do mod probe hello, and I'm going to run into an error because I need to be sudo. I need to have elevated privileges to be able to load a kernel module. And then if I look at the kernel output, I can see my hello world output, right? So this is the kernel module being successfully loaded. Okay. So the other kind of important thing that we need to make sure is that we added support for offline updates. So if we check the system D logs of the Aktualizr client, right? In this case, it's Aktualizr Torizon, we can see that it's telling us that offline updates are enabled and that we can see our TOML file is in the location where it should be, right? So this is some verification that the changes that we made to enable offline updates have been successfully applied to our device. And then this video is going to show us going through the process of creating our new image now. So again, the only thing we're going to change, I've already changed the kernel module to show Hello World v2 and showed how to change the YAML file for the new name of the image, and we're just going to call it v2, right? And it's going through the same process. It's building it's fetching um, the the baseline Torizon image from Toradex. It's applying the kernel module customization, and that's it. So we built our V2 image, and now we're gonna push the V2 image up to the Torizon cloud, right? So like I said, I just like to push all I also push the V1 just because I like to do that. It's good practice for me, so I know the transitions of all the different images that I've created. But in this case, I'm going to push my V2 image up to the cloud. And again, I'm using my credentials.zip uh, and uh, and it was successfully signed and pushed to the cloud. And we can see here if I log into my cloud instance in the browser, we can see that the OS image version 2.0, and if you see there's one more, it's 1.0. So both versions have been pushed to the cloud. So now how do we create a lockbox from here? So I'm going to show that in this video. So first we click on offline updates. We click on create new lockbox. Let me go back a little bit. All right, so clicked on offline updates on the left, create new lockbox, and I'm going to select operating system. Right, I'm going to select Calibri, the OS images that are specific to the Calibri i.MX 8X hardware type. Hit continue. And I'm only going to select the packages that I've built, right? So I'm going to select my secure offline update package. I'm going to select V2, going to give it a name. Okay, give it a name and done. I've created my lockbox. So now if I go to lockbox, I can click on the download button and I can copy this link, just copy the command, and I just need to go to my terminal, go to my PC, execute that command, right? And this is going to throw an error because I don't have an environment variable called credentials, right? So we can see that here. So Ideally, I'd set that to credentials.zip, but just for the sake of brevity, um, I'm just going to use just credentials.zip instead of the environment variable. Okay, and this is going through the entire process of retrieving all the metadata, the image itself, right? And this process just takes a fair number of minutes, which I'm not going to show here. But again, right? So now we've downloaded basically the entire image and the metadata. So now after that process is done, you'll see a directory called update, and we want to move the contents of update, right? Not the update directory, but the contents within update to the root of the flash drive, right? Because again, in our TOML config file, right, for offline updates, this is the location that we told Aktualizr where the actual update data is going to be present. So, if we wanted to be a little bit more organized, we could have specified media lockbox update, but because we didn't, we have to take all the content of update and put it into media lockbox. And so now in this video, we're going to just see that update process. So basically, like I'm going to go away, right? I have my system log just showing on the Colibri board. I'm going to plug in my flash drive. So I've copied all the contents into the flash drive, and I plugged it in, and we can see that the process is continuing, right? It's going on. It detected that there's data present under media lockbox, right? It's going through the validation process. And because there is no internet connection, right, it can't actually send status updates to the backend, and that's why we're getting these curl errors. But it's going through this update process, right? It successfully verified the image, it downloaded it, and it's going to go through the update process. Okay, and it's going to reboot now on its own. So we can see that the system is restarting. And it successfully restarted. So now, once we've restarted, let's go through the same process as before, where we want to load our hello world kernel module, right? Need to run sudo, right? And if we check the kernel log, we can see that the message is now different, which corresponds to our to the change in the kernel module. So, in summary, we saw the importance of just picking the right framework when we're selecting an OTA, framework, right? We're selecting, understanding the different considerations. We wanted to save space, we want to save time, right? So that it can be updated with minimal bandwidth. And, if we have spotty internet connection, if we're out in the middle of nowhere, we want to select a framework that doesn't require too much data to be transferred. And so OSTREE is like a great example that Torizon kind of leverages for its OTA update. And we saw, what are some mechanisms on how to handle reliability and security. We saw, and then, we saw a demo on how to actually go through the update process using Torizon. So some of the next steps that I'm personally interested in are, how do we update other software and firmware components of the OS? So what I showed in this webinar is how do we update the entire OS? So how can we update the firmware and software components of, let's say, different specific components of the OS, right? So how can we handle applications, let's say, of Docker containers, right? Onboard, let's say, coprocessor. So if you've seen my webinar on running Zephyr on with Linux on a Toradex i.MX 90 version i.MX 95, right? How can we update the firmware running on the M7 or even the M33 on this SoC? What about, like I said, I do a fair bit of work with FPGAs over a SPI bus, over a PCIe. Can we leverage this framework to be able to update the images that are present on those, right? Because if we can do that, then we have a comprehensive framework that can be pretty extensive and flexible in the sorts of updates that we can apply. So that's it. If I don't see, I appreciate everybody kind of joining. If anybody has any questions, you can put them in the chat window. All right. Looks like nobody has any questions, but yeah, if you think of any questions after the talk, you're welcome to shoot me an email if you have any questions, and I'll get back to you as soon as I can. All right. Thank you, everybody. Hope you enjoy the rest of your day. Take care.